All right, today we're going to go on a hunt for what you might call a mathematical monster. It's a problem that at first glance looks like it could just swallow numbers whole. Our mission? To see if we can tame it.
You know, some problems are kind of like mythical beasts. They seem impossibly complex, almost like they were designed to make you feel small, to make you think there's just no way forward. Well, today, we're facing one of those beasts head-on.
I mean, just take a look at this thing. This is not your everyday algebra homework, right? It's a beast with 9 different powers of x, a whole mess of unknown numbers, and it all has to somehow magically equal 0. Where would you even start?
And here it is, the monster itself. It's a 9th-degree polynomial, and degree just means its highest power is 9. See all those x values? Each one is a coefficient, basically a hidden number that defines the exact shape of this creature. Our job is to figure out what those numbers are and solve the whole puzzle for x.
But you know, every monster has a weakness, and every good mystery has a key. And lucky for us, our source document gives us the crucial clues we need to get started.
So what are we actually looking for? We're trying to find the root of this polynomial. And that's just a fancy way of saying we need to find that one special value for x that makes this entire intimidating equation balance out perfectly to 0. That's it. That's the solution to our puzzle.
Okay, so the source material gives us this list of 9 values, and they're labeled L sub q. Now, they might look totally random, but trust me, they are our secret decoder keys, and they're about to crack this whole problem wide open.
And here they are, all laid out for us from L0 to L8. Now, where these numbers come from, well, that's a fascinating story for another day. For now, all you need to know is that these are crucial pieces of evidence. This table is our treasure map.
All right, we've got our keys. Now the real fun begins. The source document lays out a very specific method. Think of it as a series of tests to check if we're on the right path. So let's follow the breadcrumbs.
Now, I'm not going to drag you through the super complex formulas themselves, because the goal here is actually pretty simple. For each test, starting from k equals 0 and going all the way up to 9, we're going to plug in our decoder keys. If the answer is 0 every single time, it proves our keys are the right ones, and we can unlock the next stage of the puzzle.
So, we begin with the first test, for k equals 0. We run the numbers, apply the formula using our keys, and, what do you know? It works. We get a perfect 0. The first key fits the lock.
Okay, on to the next test, for k equals 1. The calculation gets a bit more involved this time, pulling in more of our keys, but the result is exactly the same, 0. Again, the pattern is holding up.
And this just keeps happening. The source document confirms that for every single value of k we test, all the way up to 9, the result is 0. This isn't a coincidence, this is confirmation. We've cracked the code. We are absolutely on the right track.
So what was the point of all that testing? Well, it was the key to finally unmasking our monster. By proving our decoder keys were correct, we've basically forced this polynomial to reveal all its secrets. We can now figure out what those hidden s coefficients actually are. Remember this guy? With all those unknown s values that looked so intimidating? Well, thanks to our little verification process, they are not a mystery anymore. We're about to see this thing's true face. And, get ready for this, here they are. Just look at that. The simplicity is kind of shocking, isn't it? Almost every single one of those coefficients is just 0. The only one with any value at all is s2, which is 6. All that perceived complexity was hiding a very, very simple core.
So what does it mean when a coefficient is 0? Well, think about it. In any equation, any term that gets multiplied by 0 just becomes 0. It disappears. So all those other parts of the polynomial, the x to the 8th power, the x to the 7th, and so on, poof, they just vanish into thin air.
And this is what we're left with. The monster has been tamed. Our terrifying polynomial has been reduced to this simple, clean, 2-term expression, x to the 9th minus 6 times x to the 6th equals 0. It is the very same equation, just with its scary mask pulled off.
We've simplified the problem in a huge way, but we still haven't found the root, have we? So what is that special value of x? Well, the source document reveals one last beautiful shortcut.
After all that work, do we still need to wrestle with a bunch of complicated algebra? Nope. The answer is surprisingly elegant, and it's been hiding in plain sight this entire time.
Remember our very first decoder key? That first piece of evidence we were given at the start? The document points us right back to it. The solution has been there all along, just waiting for us.
And here is the really elegant trick. You take that first key, the number 54, and you just divide it by the degree of the polynomial, which was 9. The answer? It's 6. One of the roots of that massive, monstrous equation is simply 6. It's an absolutely beautiful end to a complex journey.
And that really brings it all home, doesn't it? We started with a problem that looked impossibly complicated, a true mathematical monster. But with the right keys and a clear method, we uncovered the simple truth hiding underneath. It's a perfect reminder that the goal, so often, isn't to wrestle with complexity, but to find the elegant simplicity right there at its core.